Hello ladies and gentlemen, it's Miss Skokan and we're in section 3.4 now, factoring polynomials. As always, we're going to start with a little warm-up and I'd like you to pause the video now, factor and multiply. Turn the video back on when you're ready to check your answers. If you got any of these wrong, pause the video, go back and check your answers and see if you can figure out how to get the correct answer. If you cannot, remember to put a post-it note in your notes and then ask me when we are back in class together. We have the objectives for this lesson. Use the factor theorem, that's something new for us, to determine the factors of a polynomial, and factor the sum and difference of two cubes. So we know that when we divide a number, if the number goes in evenly, then that means we're going to have a remainder of 0. It's the same with polynomials. So if we have a factor of the polynomial and we divide the polynomial by its factor, we will get a remainder of 0. This is the remainder theorem. So pause the video now so that you can read the remainder theorem. You also have it in your notes. Make any additional notes that will help you remember what it means, and we'll see how to use it in just a minute. Okay, we have a couple of examples to work on, and what we're going to do is try to determine whether the binomial is a factor of the polynomial. And the way that we're going to do it is we're going to use synthetic division. So first things first, we need to figure out what number to put in the box. Remember that the format is x minus a. So in example A, the number that's going to go in the box is -1. In example B, the number that's going to go in the box is -2. So with synthetic substitution or synthetic division fresh in your mind from the previous lesson, you can fill this out and determine that we end up with a remainder of 5. Because we have a remainder of 5 and 5 is not equal to 0, then we know that x plus 1 is not a factor of this polynomial. Pause the video now and using this same procedure, practice with example B, and then turn the video back on when you're ready to check your answer. After doing the synthetic substitution for example B, we found that we did get a remainder of 0. So that means that x plus 2 is a factor of the polynomial p of x. Now we're going to learn a little bit more about this in the next section as well. So hold tight, just learn this procedure for now, and we'll take a look at some how to find a factor like x plus 1 or x plus 2 of the polynomial in the next section. All right, the title of this section is Factoring Polynomials, so we're going to be factoring. We already know some great methods for factoring quadratics, and we're going to use some of those same procedures for factoring polynomials. So let's take a look at an example. You have this example in your notes, and in this case what we want to do is factor by grouping. So we're going to group together the first two and the second two factors, or terms, I should say. And when we do that, we determine that we end up having a common factor between the two groups of x minus 1. So we pull that out as a common factor, and we end up having x minus 1 times x squared minus 25. Immediately we recognize x squared minus 25 is a difference of squares, and we factor that further for our final factored form of x minus 1 times x minus 5 times x plus 5. We can use the table feature on the graphing calculator to determine this, and one thing that we can do is we can put in both the original form of the polynomial and the factored form of the polynomial under y1 and y2, and notice that the table looks exactly the same for every value of x. Y1 and y2 are equal to each other. Now, the only thing that we can do is determine that these are equal to each other, but unless we look at every single possible value of x as an input to the function, the only thing that we can observe is the ones that we see. So we do see that the ones that are visible to us or that we choose to look up on our table on our calculator show the same function or y values for each x value. You may have noticed in your vocabulary and your notes that we're going to be factoring not just difference of squares, but the sum of cubes and the difference of cubes. And you might suspect that there's a pattern for us to memorize, and there is. So it's going to benefit us to memorize both of these patterns so that we don't have to search how to factor these and we don't make mistakes with factoring a binomial. Factoring the sum of cubes and difference of cubes has a specific pattern that if we always follow, we're never going to get it wrong. So let's take a look at an example. Now you notice with this example, the first thing that we see is we do have a common factor, and the rules of factoring are all followed by the first rule, which is factor out any GCF, any greatest common factor you have. So our greatest common factor in this example is 4x. We factor out the 4x, and then we see that we have a sum of cubes because x cubed is a cube, perfect cube, and 27 is a perfect cube. So we're going to set it up so that we see them as cubes. Now it's going to be easier for us to follow the pattern. And following the pattern, we end up with this set of three factors, or you could look at it as four factors: 4, then x plus 3, and then x squared minus 3x plus 9. Now you may be tempted to factor further the x squared minus 3x plus 9, but that's non-factorable, and we'll continue to see that as we factor sum of cubes and difference of cubes. You have another example in your notes, example B, so I'd like you to pause the video, try this one out. Remember to show it first. Well, first look for GCFs, and after you determine whether, factor out any GCFs or determine you don't have any GCF, then show each of the terms as a perfect cube and then use the pattern. Turn the video back on when you're ready to check your answer. Here's the result of our factoring using the pattern for difference of cubes. If you have any question about how this works, stop by for extra help or ask in class. Okay, we've got something of a real-world example in example 4, and it's a geometry application. We have a plastic box. We have the function for the volume of the box, and we want to determine the values of x. What we really want to be able to do is factor this polynomial. So one of the things that we're going to use to do that is if we know any of the factors, then we can use either long division or synthetic division to divide out that factor. What we're going to be left with as our quotient is called a depressed polynomial. And then we can continue to factor that further. But we just really need one to start with so that we can get hopefully into a quadratic that is factorable, or we can use the quadratic formula. That's kind of our goal with these polynomials. So first things first, let's take a look at the graph. We see that the graph has 3 x-intercepts. We know that that means that there are 3 real zeros for this function. So we're going to start with one of those, and it doesn't really matter which one. We can start with any of them to determine the others using synthetic division. So we see that one factor is x equals 1. And so what we're going to do is put 1 in the box, use the coefficients as we always do with our synthetic division, and we're going to factor the polynomial in this way. Notice that we end up with a remainder of 0. So we know that x minus 1 is a factor of the polynomial, and we also know that we end up with this, what we call a depressed polynomial of x squared plus 7x plus 10. Now, our next step is going to be to look at that remaining quadratic factor and see if it's factorable. If it's not factorable, we can use the quadratic formula. If it is factorable, we're going to factor it. And in this case, it is factorable. So we factor it, and we have all of our factors for the volume the volume function of this plastic box. Okay, so we are done with our lesson 3-4, factoring polynomials. We'll see you back again for lesson 3-5, finding real roots of polynomial equations, where we will learn what to do with those depressed polynomials and actually how to find that very first one to get us started with synthetic or long division. See you next time.